acid-base properties of ions and salts. So some ions will act as bases. The hydrogen carbonate ion that we saw in the table of weak bases is one of these. It can react with the water molecule, taking a hydrogen ion, a proton from that, to form H2CO3 and hydroxide ion. So hydrogen carbonate ion acts as a base. You can't have just hydrogen carbonate ion though, right? There needs to be a counter ion. Nature does not like it when charges get separated. So in the solution, you've got negative ions, but you also have positive ions. We call those counter ions. They're just balancing the charge. When you have the ion and a counter ion, that's called a salt. Basically, it's just an ionic compound. It's a salt. So sodium hydrogen carbonate is a soluble salt, and it will form sodium ions and hydrogen carbonate ions. So if we have a solution of sodium bicarbonate, sodium hydrogen carbonate, the solution will be basic. The sodium ion is not going to do anything, but the hydrogen carbonate ion can take a hydrogen ion from water and make hydroxide. Any questions? Hydrogen carbonate ion is the conjugate base of this acid, of this carbonic acid. So any anion can be thought of as the conjugate base of an acid. So in general terms, we think of A- as being the conjugate base of the acid HA. The acid loses a proton, it becomes this anion. So a specific example would be nitrate ion. Nitrate ion is the conjugate base of nitric acid. Remember, conjugate acid-base pair differ by a proton, one hydrogen ion. So we can think of any anion as the conjugate base of an acid, but not every anion will actually act as a base. Depends on how strong that acid is. If that conjugate base, if it's the conjugate base of a weak acid, it will be a weak base. If it's the conjugate base of a strong acid, though, it's going to be pH neutral. It's not going to affect the pH. So the weaker the acid, the stronger the conjugate base. So chloride ion. Chloride ion is the conjugate base of HCl. But HCl is a strong acid. So when we put HCl in water, it ionizes completely to hydrogen ions and chloride ions. This is the conjugate base, but this reaction never goes in the other direction because chloride does not have a strong affinity for hydrogen ions. That's why it comes apart so completely. But if we look at fluoride ion, that's going to be basic because HF is a weak acid. So when hydrogen fluoride is dissolved in water, it gives a proton to the water molecule forming hydronium ion and the fluoride ion. But this is an equilibrium, and the equilibrium actually lies to the left. So fluorine can react with hydrogen ions or with water molecules to reproduce the original acid. That make any sense? Can I rephrase? I think I can. So when a strong acid ionizes, it ionizes completely. This is not an equilibrium, it goes in one direction only. When a weak acid ionizes, it forms an anion, but this is an equilibrium and it goes in both directions. maybe, might be better if we show it without the water molecule in there. Oops. So a base will neutralize acid, right? So adding adding chloride to hydrogen ions should neutralize them. But this reaction doesn't go in the reverse direction. Fluoride ions and hydrogen ions will combine, and they'll combine to form a weak acid. This is the conjugate base of the weak acid. This is the conjugate base of a strong acid. It cannot act as a base.
Okay, so then would it be safe to assume that the weak acids are not always at equilibrium?
Weak acids will always be in equilibrium, yes, or going to equilibrium. So the weak acids always have the double-headed arrow. The strong acids have the single direction arrow. Yeah.
Well, I was going to say, is there a particular reason why hydrogen doesn't have or chloride doesn't have an affinity for hydrogen, or is it just natural occurrence?
We're going to talk about that. We're going to talk about why some acids are stronger than others, but not yet. Any other questions? Yeah.
Is it the same case with weak and strong bases as well?
Yep. So the weaker that this acid is, the more this equilibrium lies to the left, making the conjugate base stronger. If this is a stronger acid, then the conjugate base is weaker. So it's an reverse thing. If the pH is high, the pOH is low. If the pH is low, the pOH is high. So here are some ions and acids. So here we're looking at acid strength increasing. So here we have strong acids, HCl, H2SO4, HNO3. And over here we have the conjugate bases. So chloride is the conjugate base of a strong acid. Hydrogen sulfate, conjugate base of a strong acid. Nitrate. So these are not going to react as bases at all. They're just going to be neutral. When we get into the weak acids, their conjugate bases will be weak bases. And down here, if we look at the strong bases, these are their conjugate acids, and those really do not act as acids. And just notice the difference between these guys is one hydrogen ion. You take a hydrogen ion off of this acid and it becomes the conjugate base. Here, Cn minus, put a hydrogen ion on it and it becomes the conjugate acid. Classify each anion as a weak base or pH neutral. What we want to do is look at the conjugate acid of this ion and identify, is it strong or weak? So CHO2 minus, what's the conjugate acid of that? No, it's not acetic acid. But we're going to slap a hydrogen ion on there, and we'll get CH2O. Yeah, I put the 2 in the wrong place. CHO2, sorry. I was thinking of formic acid. Is that weak or strong? It's weak. How do we know? Because it's not strong, right? There's 6 strong acids and everything else is weak. So if this is a weak acid, this is the conjugate base of a weak acid. Does it act as a base? Yes, it does. So this would be a weak base, that ion. HClO4, what's its conjugate acid? Perchloric acid, HClO4. Strong or weak? That's a strong acid. So if this is a strong acid, what can we say about this anion? It's going to be pH neutral. Does that make sense? Kind of? Anions can also, I'm sorry, we were talking about anions as weak bases. How do we determine the pH of that solution? Well, we can figure it out if we know what Kb is for that anion that acts as a weak base. So there's a relationship between Ka and Kb. So let's look at this guy. So that's an acid. So Ka is going to equal the hydronium ion concentration times A minus divided by the weak acid concentration. And here we have that same anion acting as a base. So we can write Kb is going to equal hydroxide ion concentration times Ha divided by A minus. Now I'm going to multiply those two together. So we'll look at Ka times Kb. Some things are going to cancel out. The A minus is going to cancel out, and the Ha is going to cancel out. And we're left with the concentration of H3O plus times the OH minus concentration. And what do we call that? Kw. That's the autoionization of water. Kw is H3O plus times OH minus. Any questions? Ka times Kb is going to equal Kw, which is 1 times 10 to the minus 14. If Ka is a bigger number, that means Kb must be smaller in order for the product to remain the same. So find the pH of a 0.250 molar NaC2H3O2 solution. Ka is 1.8 times 10 minus 5. This is sodium acetate. The sodium is just a counter ion, and so we're going to leave it out of our equation because it'll make things look simpler. So C2H3O2 minus plus H2O. It's going to take a hydrogen ion from the water and leave us hydroxide ion. So to find the pH of this, we're going to need to make an ice table. So in 1 mole of sodium acetate, there's 1 mole of acetate ions. So the acetate ion concentration is just the 0.250 to start with. And what would be our acetic acid concentration initially? 0. And how about hydroxide? Basically 0. Huh. There's just way too many puns in this chapter. So then this is going to change by negative x, and this will be plus x, or plus plus.
Plus T.
Plus t. It was an x that just was falling over.
I was doing a cartwheel.
Yeah, I was doing a cartwheel. And so KB is going to equal x squared over 0.250 minus x. But we weren't given KB. KA times KB equals KA. KW. There's too many Ks. Right. So this KB that we're looking for times the KA, 1.8 times 10 to the minus 5, is going to equal 1 times 10 to the minus 14. So I'm going to take 1 times 10 to the minus 14, and we're divide by Ka, 1.8 times 10 to the minus 5, and I'm going to get 5.55 repeating times 10 to the minus 10. Now technically that would have 2 sig figs, but let's keep a couple extra 5s to avoid any rounding errors. Here we have a small equilibrium constant and a relatively large initial concentration, so we can probably do the x is small thing. We'll just say that that's essentially 0. And so x is going to be equal to the square root of the product here. times 85 times 10 to the minus 5. If we divide that by 0.25 or multiply by 100, I get 0.005%, so plenty small. So sometimes I get all caught up in solving for x and everything, and then when you get to x and you're like, wait, what was I doing? Oh, I'm looking for the pH. Well, this is the hydroxide ion concentration. So the previous 2 examples, what I did is I used this and calculated pOH and subtracted it from 14. The other way to do that is to find hydrogen ion concentration is going to be 1 times 10 to the minus 14 divided by the hydroxide ion concentration. .485 times times 10 to the minus 10. And then pH is the negative log of that. .07. Thank you. Any questions? Is that a reasonable pH for a solution of an anion acting as a base? It should be basic, right? It should be higher than 7, so that's good. 9.07. So which of these anions will act as a weak base? Yeah, it's going to be C. Because this is the conjugate base of a strong acid, conjugate base of a strong acid, conjugate base of a weak acid. So that makes it a weak base. So anions can act as weak bases, cations can act as weak acids. There are actually 3 different categories here. So the first one we'll look at is cations that are counterions of strong bases. So these cations are going to be pH neutral because the strong bases dissociate completely. And so just like the conjugate bases of a strong acid, these are not going to act as acids. So examples would be the alkali and alkaline earth metals. They're going to be pH neutral. So a cation can be formed from a non-ionic weak base by adding a proton to its formula. So here's the base would be B, and we've added a proton. That makes a cation, and this is a cation derived from a weak base. And so it can react with water to form hydronium ion and the base again. So this is a cation that is the conjugate acid of a weak base. A conjugate acid of a weak base is a weak acid. The weak and strong and acid and base and conjugate, I mean, it's just like all over the place. So you just kind of have to take a moment and think about it, right? In order for this to act as an acid, right, it has to be able to hold on to that proton, at least somewhat. If this was a strong base, the reaction, this reaction wouldn't occur. So again, if we're going to calculate the pH of a solution like this, we're going to have to use Ka, which won't be given because we're looking at a weak base, and so they'll give us Kb. And the third group is small, highly charged metals. So metal ions like aluminum 3+ and iron 3+. Look at the periodic table, and aluminum is in period 3, iron's in period 4. They're fairly close to the top of the periodic table, so they're smaller, and they have a large charge, +3. So what happens to these guys is that the ion becomes hydrated. So the ion will associate with 6 water molecules and form this complex ion. We'll learn more about how that happens later. But this hydrated ion can act as a Bronsted-Lowry acid. So Bronsted-Lowry acid is going to donate a proton to the base. Yeah. And this looks all weird, doesn't it? Because what happened here, here we had a +3 charge. Now we have a +2 charge because we took a hydrogen ion off. And we can't keep these H2Os all grouped together as 6 because one of them isn't H2O anymore. So there's 5 H2Os and an OH. And that proton went over to the water. So here, aluminum ion can act as a weak acid. Fe3 plus can also do that. These are the only two that I would expect you to remember. And I'm not going to ask you to discuss or explain why they act as weak acids. You are only responsible for knowing that they do. Fe3 plus, Al3 plus, those will act as weak acids. So we should be able to answer questions like this. Classify each cation as a weak acid or as being pH neutral. Just like with the anions, what we're doing is we're looking at the conjugate of these guys, right? This one's a little bit hard because how's that going to lose an H plus? But what does this come from? What acid or base would lithium ion come from? Lithium hydroxide. Is lithium hydroxide a strong base or a weak base? It's a strong base. So then this ion, this counter ion of the strong base is going to be pH neutral. How about this one? You see the N in there? So this is like ammonia. You can treat it like ammonia. It's just got a little something different hanging here instead of a hydrogen ion. So if I take a hydrogen ion off of that, CH3, NH2, this is going to be the base. Weak base or strong base? This is a weak base, right? All of those things with the nitrogen are weak bases. Is this going to act as an acid or be pH neutral? It's going to act as an acid. How about Fe3 plus? It's a small, highly charged metal. Therefore, Mrs. K said it will act as a weak acid. Okay, so we also need to be able to look at a salt, which is a cation and an anion, and identify, will this solution be acidic, basic, or neutral? And so we have to look at each of the ions separately and identify what they're doing. So if we have a salt where neither the cation nor the anion acts as an acid or a base, then that solution will be pH neutral. So these will be things where the cation is a counterion of a strong base. The anion is the conjugate base of a strong acid. So things like sodium chloride, calcium nitrate, potassium bromide. So let's just look at this guy. So we want to think, well, what are the two ions in there? Well, there's K plus and there's Br minus, right? Well, this is related to which acid? Put an H on it. HBr, right? Is that strong or weak? Strong. What kind of a base would K plus come from? A strong base, KOH. I saved it. I started to write acid. So the stronger it is as a base, the weaker it is as an acid, and vice versa. So here, the base is strong, and that makes the conjugate nothing. Here, the strong acid, the conjugate is nothing. It's not going to act as a base. The conjugate is not going to act as an acid. Any questions? Yeah.
Can you explain again why the strong ones doesn't ionize water?
Yeah. So if we look at HBr. And then, so what we're wanting to know is, will this act as a base? So in order for this to act as a base, it has to form HBr molecules in the solution. But HBr is a strong acid. All of the molecules ionize. They're all separated. So this is not going to happen. Does that make sense?
Yeah.
Because these guys don't exist. In a solution of HBr, there's no HBr. There's hydrogen ions and there's bromide ions, because that's the definition of a strong acid. HCl, there's hydrogen ions and chloride ions. The chloride ions are not going to react with some hydrogens to form HCl, because the strong acids are not found as molecules in solution. Okay? I think that was a little better than the previous explanation. We can also have a salt where the cation does not act as an acid and the anion does act as a base. So these are going to form basic solutions. I think in some ways, categorizing these makes it more confusing. So let's just look at one of these. What are the two ions? Well, there's K plus and there's NO2 minus. So we're wanting to know if this is going to act as a base. What's the conjugate acid? It's HNO2. Strong or weak? Weak. So this will act as a base. And maybe we can look at this in the same way here. So here's what the acid does. It's a weak acid, so it's in equilibrium here, the ionized form and the non-ionized form. There's actually more of the HNO2 molecules than there are of the NO2 minus ions in the solution. So if we're looking at NO2 minus, will react with water to form HNO2? Yes, it will, because this goes both ways, right? There is a significant amount of HNO2 molecules in that acid solution, whereas with the strong acids, there weren't any. So this can act as a base because it's the conjugate of a weak acid. Does this act as an acid? What's the conjugate base? It comes from KOH, right? So potassium does not act as an acid or a base, it's neutral. So we have one ion that's pH neutral and one ion that acts as a base. The overall solution will be basic, right? We can have the reverse. Well, let's look at this guy, FeCl3. So we've got Fe3 plus ions, and we have chloride ions. Do Fe3 plus ions act as weak acids? Yes. Why? Small, highly charged metal ions, Mrs. K said they did. A lot of other people say they do too. So this is going to act as an acid. What about chloride? No, because for chloride to act as a base, chloride reacting with the water would have to make HCl. But HCl is not found as an intact molecule in solution because it's a strong acid. So this one's neutral. So this solution then would be acidic, right? Because one of them acts as a weak acid. So I think instead of, trying to rememberize, instead of trying to memorize things like this, which is so easy to swip. Gosh, it's only Wednesday. Switch the words, strong and weak, acid and base, etc. I think it's better to just look at the individual ions and think, what acid or base is this related to? Is that thing strong? If that thing's strong, what I'm looking at is nothing. It's pH neutral. If the acid or base my thing is related to is weak, then my thing will also be a weak something. And then we have the last possibility, where you've got a cation that's acting as an acid, and you have an anion that's acting as a base. So one's making the solution more acidic, one's making the solution more basic. So overall, what's the solution going to be? It depends on who's stronger. The stronger one will win. So look at the Ka of the acid and the Ka of the base. The larger K value will dominate. So this summarizes all of that. So let's practice these. Determine if the solution formed by each salt is acidic, basic, or neutral. So I'm going to take this and separate it into its ions. The metal ion by itself and what's left. Now, this can go on and lose a hydrogen, but we're not gonna split this into 3 ions here, we're just gonna do 2. Okay, so we've got sodium ion and we've got hydrogen carbonate ion. Is sodium ion, does it act as an acid or a base? It's neutral, because it's related to sodium hydroxide, a strong base. So that's not gonna do anything. This is the conjugate base of a weak acid, right? It's the conjugate base of H2CO3, which is a weak acid. So it will act as a base then, right? So this solution would be basic. Let's look at the second one. Well, here we have a nitrogen and some hydrogens and then this other stuff. And here's chlorine. So chlorine is the anion. Is that going to be acidic or basic? No, because it's related to a strong acid. Is this related to a weak base? Yes, it is. We take the hydrogen off, we get a weak base. This is the conjugate acid of a weak base. So this solution is acidic. Well, KNO3. Neutral. Potassium from potassium hydroxide, a strong base. Nitrate from nitric acid, a strong acid. So this one will be neutral. And then here we have Fe3 plus and NO3 minus. I guess I should mark those off. Those don't do anything. Well, we already identified nitrate is the conjugate base of a strong acid, so it's not going to do anything. And what about that guy? That'll be acidic. Yes?
On the previous slide, the examples for like the ones that has both.
Mm-hmm.
This one, so like if it's like FE, F3,
Mm-hmm.
do we multiply the K with 3? Because there's 3.
No,
No?
no.
Okay.
You don't multiply. So if we look at this one, when that forms ions, it's going to form Fe3 plus, and yes, it's going to form 3 fluoride ions. But when those fluoride ions go to act as a base, right, it's just that you have 3 times as many of them. That doesn't affect the equilibrium constant. So that's trying to make a strong acid. It's not going to happen. So yeah. I'm sorry. That's not a strong acid. It's a sneaky one, HF. This is a weak acid. So this is a weak acid, so this does act as a base, and this acts as an acid, right? From the information we have right here, we can't tell what the solution will be. We'd have to know the Ka for this and the Kb for that, which we could go look up, but do you want to do that? I don't. Any other questions? We didn't do this one, did we?
No.
No. It's just, these ions are all like blurring together. So, this has ammonium ion and bromide ion. This is related to NH3, right? Is NH3 a weak base or a strong base? It's a weak base. So then this will act as a weak acid. Br minus is related to which acid? HBr, which is a strong acid. So that's not going to do anything. So the NH4 plus will act as a weak acid, and so we should get an acidic solution. KCl, got potassium ions and chloride ions, neutral. And NaHCO3, does this act as an acid? No, because sodium hydroxide is a strong base. This can act as a base. I'm sorry. Yes, that's right. It's confusing because it can also act as an acid, but we don't want to go there. So that's not going to do anything. These aren't going to do anything. This will act as a base, so this solution would be basic, but it's asking which of them forms an acidic solution. So that would be the answer.